Something changed on June 29th, 2022. Not in the news, not in the weather, not in anything you could see from your window or feel beneath your feet. What changed was the planet itself. Earth completed one full rotation around its axis in less time than it had ever done since human beings began measuring such things with instruments precise enough to catch it. The day was shorter than normal, not by hours, not by minutes, not even by a full second, by 1.59 milliseconds. You cannot feel a millisecond. You cannot see one. If someone reached into your morning and quietly removed 1.5 milliseconds from it, you would go about your entire day completely unaware. You would drink your coffee, sit in traffic, lie down at night, and never once suspect that the ground beneath you had moved through its rotation fractionally faster than it was supposed to. The human body has no instrument sensitive enough to register that kind of change, but we built something that does. And when it caught that number, and then caught it again and again across multiple years in a row, with each year producing some of the shortest days ever logged in the modern record, the people who spend their lives watching the rotation of this planet quietly set aside whatever else they were working on and began asking a question that has no comfortable answer. Why is Earth speeding up? That question sounds simple. It is not. To appreciate why it unsettles the researchers who study it, you need to understand something that most people were never taught in school. The length of a day is not a fixed number. It never was. The 24 hours on your phone, the tidy division of light and dark that organizes every schedule, every flight, every power grid on this planet, that number is an average, a useful fiction, a rounding. The actual length of time it takes Earth to complete one rotation has always fluctuated, nudged and pulled by an invisible orchestra of forces acting on it from above, below, and within. Tides, wind, the slow creep of ice, the churning of iron in the dark. All of it leaves a fingerprint in the rotation data, and all of it has been carefully cataloged and studied. What researchers expect when they look at the long arc of Earth's rotational history is a planet that is very, very gradually slowing down. The moon is responsible for that. Every day, the gravitational pull of the moon tugs at Earth's oceans, raising and lowering the tides in a cycle that has been running since the moon first formed from the debris of an ancient collision roughly 4.5 billion years ago. Those tides are not free. They cost something. The friction of water moving against the ocean floor, the dissipation of tidal energy in coastal shallows. These forces act as a brake, a gentle, almost imperceptible brake, but a brake nonetheless. Across hundreds of millions of years, that brake has been working. Ancient coral fossils tell us that 400 million years ago, a year had more than 400 days in it. The days were shorter because the planet was spinning faster. Over time, tidal drag slowed things down. The days grew longer. The moon crept outward. The system settled into its long, slow deceleration. That is the expected direction of travel. Slower. Always. On geological timescales. Slower. Which is why what started showing up in the data around 2016 made researchers stop mid-sentence. The trend reversed. Not dramatically. Not in any way that would reshape your morning or shorten your commute. But measurably, consistently, and in defiance of what the models predicted should be happening, Earth began spinning faster. Year after year, the planet logged some of the shortest days ever recorded in the era of atomic precision. 2020 broke the record that had stood for decades. 2021 broke it again. 2022 shattered it entirely with that number on June 29th, 1.59 milliseconds ahead of schedule, printed in the data like a question mark pressed into stone. Here is what makes this genuinely strange. The force that causes the long-term slowing has not stopped. The moon is still there. Tidal friction is still operating exactly as it always has. The brake is still engaged, but something else has entered the system, pushing in the opposite direction with enough force to overcome it. Something that is not in the standard models. Something that reaches, depending on which theory you follow, from the frozen surface of Greenland all the way to the molten iron heart of the planet. And when you start pulling on that thread, when you follow the physics from the surface down through layer after layer of Earth's interior, you find a story that is far stranger and far more consequential than a millisecond would suggest. Let us begin at the most fundamental level. What does it actually mean for a planet to spin faster? Picture a clock. Not a digital display, not the clock on your phone, but the planet itself, turning once every 24 hours, illuminating different faces of itself toward the star above, in a slow, majestic rotation that has been running without interruption for longer than complex life has existed. That rotation is not a simple mechanical process. It is the sum of an enormous number of competing forces, some pulling the rotation faster, some dragging it slower, some acting over millions of years, and some acting over a single afternoon. The crust sits on top of the mantle. The mantle floats above the outer core. The outer core wraps around the inner core. None of these layers rotate at exactly the same speed. They are coupled to each other through pressure, gravity, and electromagnetic force, but loosely. Changes in one layer transmit to the others over timescales ranging from years to decades to centuries. The rotation you experience standing on the surface is not simply the rotation of the planet as a unified object. It is the rotation of the outermost layer of a system in which every layer is in constant, slow negotiation with every other. When something changes deep inside that system, the surface eventually feels it. And here is the part that should make you pause. The changes being detected in the rotation data are not coming from one place. They are not caused by a single identifiable mechanism that scientists can point to and say, there, that is the culprit, we understand it, we have it contained. The acceleration being measured right now at Earth's surface appears to be the result of multiple systems changing simultaneously. The ice at the poles is melting and redistributing the planet's mass. The atmosphere is shifting its angular momentum in response to ocean warming. The ocean circulation itself is changing in ways that alter how momentum is transferred between the fluid Earth and the solid Earth. And beneath all of it, in the place where no instrument has ever reached, where the pressure is 3 million times what you feel right now on your skin, where iron exists in a liquid state at temperatures that exceed the surface of the sun, something moved, something changed direction. And the effects of that change are still traveling upward through the layers, arriving at your feet decades after they began. A millisecond, it turns out, is not a trivial thing. Consider what is built on the assumption that time flows at a predictable rate. Every satellite orbiting this planet broadcasts a timestamp. Those timestamps are what allow your phone to know where you are, allow aircraft to land in zero visibility, allow container ships to navigate narrow straits in the dark. Those satellites do not measure the ground directly. They measure time, and from time, they calculate position. When Earth turns faster than the satellites expect, the ground moves ahead of the prediction. The error is small, a few centimeters in most cases. But a few centimeters is the entire tolerance margin for a surgical robotic system, for a precision-guided landing approach, for a tunnel being drilled simultaneously from both ends that must meet in the middle to within acceptable tolerances. Or consider the financial system. Stock exchanges in New York and London and Tokyo execute millions of transactions every second. Each transaction carries a timestamp accurate to the microsecond. Those timestamps are synchronized to a global time standard anchored to atomic clocks. When the planet beneath the clock starts moving ahead of schedule, the synchronization between Earth time and atomic time begins to drift. And in a system where the sequence of events determines who owns what and who owes whom, a drift in the timing of events is not a technical curiosity. It is a liability measured in real money. Or consider the power grid. Alternating current flows at a fixed frequency, 50 or 60 cycles per second depending on where you live. Grid operators synchronize their regional networks to a global time standard to balance load across thousands of miles of interconnected infrastructure. When the time standard and the planet disagree, the balancing signal contains noise, small amounts of noise, carefully managed. But noise in a power grid is not abstract. It is the difference between a stable system and one that is operating closer to its failure margins than the engineers who designed it ever intended. These are not hypothetical concerns. The engineers who maintain these systems have been running the numbers, and what they are finding quietly in technical bulletins and internal analyses and papers published in journals that most people never read is that the planet is requiring more correction than it used to. The updates are more frequent. The margins are being consumed faster. The assumption that Earth behaves within a predictable range is an assumption that is being tested in real time. And the deepest, unsettling truth underneath all of it is this: we do not yet fully understand why it is happening. The measurements are clear, the instruments are calibrated, the signal is real, and it has been independently verified by teams on different continents using different methods. But the explanation, the complete unified story of why this particular planet on this particular rock is spinning faster than it has in 50 years of careful measurement, that story is still being assembled, piece by piece, layer by layer. From the frozen surface of disappearing ice sheets to the liquid iron interior of a world that has been keeping its own time since long before anything alive was around to notice. That story begins with a clock. A specific kind of clock. A clock so precise it would not gain or lose a single second across 300 million years. And what happened when scientists finally had an instrument that accurate and pointed it at the planet is where everything described above starts to make a different kind of sense. If the idea that the ground beneath you is moving faster than it should, that the clocks built to track the universe are drifting away from the clocks built into the rock, that a millisecond can carry consequences measured in power outages and financial liability and the accuracy of the device guiding a surgeon's hand, if any of that unsettles you the way it unsettles the researchers who live inside this data, then stay. Because the deeper this goes, the stranger it becomes. And what is waiting at the bottom of this story, in the iron dark at the center of everything you stand on, is the kind of thing that makes scientists go quiet for a moment before they answer. The instruments are running, the data is coming in, and we are only just beginning. Before 1955, the most accurate clocks on Earth were losing or gaining roughly 1 second every 300 years. By the standards of daily life, that was extraordinary. By the standards of a civilization that was beginning to build satellite networks, coordinate global financial systems, and navigate aircraft across ocean distances in zero visibility, it was nowhere near good enough. Time, it turned out, was not something the world had ever truly measured. It had only ever approximated it. And the approximation, for most of human history, was sufficient because nothing we built required anything better. Then a physicist named Louis Essen, working at the National Physical Laboratory in England, built something that changed the relationship between human civilization and time itself. He built the first practical atomic clock, and when it was switched on, the world discovered that it had been keeping time wrong for its entire existence. The principle behind an atomic clock is not complicated to describe, though it is staggering to contemplate. Every atom of the same element anywhere in the universe vibrates at exactly the same frequency, not approximately the same, not close, exactly identical. A cesium-133 atom in a laboratory in Paris vibrates at the same rate as a cesium-133 atom in a laboratory in Tokyo, in a crater on the moon, in the outer arm of a distant galaxy. The universe does not allow variation. It is one of the deepest regularities written into the structure of physical reality, and it means that an atom is not just a building block of matter. It is a clock, a perfect, universal, incorruptible clock that has been running since the moment it was formed and will keep running until the conditions that sustain it no longer exist. Cesium-133 atoms oscillate 9,192,631,770 times per second. That number is not an approximation. It is the definition. In 1967, the international scientific community redefined the second itself, not as a fraction of Earth's orbit around the Sun, not as a fraction of a day, but as exactly that many oscillations of cesium-133 radiation. The planet was removed from the equation. Time was anchored to physics. The result was a clock so accurate it would not gain or lose a single second across 300 million years of continuous operation. And with that level of precision suddenly available, scientists could do something they had never done before with any real confidence. They could measure the planet, not estimate it, not approximate it, measure it, with the same ruthless precision that the universe applies to its own atoms. What they found was unsettling from the beginning. Earth's rotation, when examined under the unforgiving lens of atomic precision, turned out to be a mess. It fluctuated constantly. It speeded up in the northern winter as atmospheric mass shifted toward the poles and the planet pulled itself fractionally inward, conserving angular momentum the way a spinning skater does when drawing in their arms. It slowed in the northern summer as that mass redistributed outward again. Major earthquakes left detectable signatures, sudden small adjustments in the rotation rate as stress was released along fault lines and mass was redistributed in the crust. El Niño events, those large-scale reorganizations of tropical ocean heat that ripple outward into weather patterns across the entire globe, produced measurable rotation anomalies as the atmosphere shifted its angular momentum in response to changing sea surface temperatures. Large accumulations of snow at high latitudes added their own faint signal. Changes in ocean circulation contributed theirs. All of this was noise layered on top of signal. Complicated, overlapping, interacting noise, but noise that could be cataloged and understood. Scientists identified the sources of the fluctuations one by one. They built models that could account for them. They developed correction procedures that kept the official global time standard, coordinated universal time, in alignment with the planet's actual rotation to within fractions of a second. The system worked. It was imperfect in its details, but stable in its overall behavior. The planet was messy, but it was predictably messy. Its fluctuations fell within a range that the models could describe and the infrastructure could absorb. Then came the data from 2016 onward. The fluctuations were still there. The seasonal patterns were still there. El Niño signatures, atmospheric angular momentum shifts, all of it was still in the data, exactly where it was supposed to be. But underneath all of it, emerging from the noise like a face appearing slowly through fog, was a signal that did not belong, a trend, not a fluctuation that would correct itself when the season changed or the ocean cycle reversed, a sustained, consistent, multi-year departure from the expected baseline, moving in one direction. The average length of a day was shrinking. Year after year, the daily averages were falling. The planet was spinning faster. The first response in the scientific community was exactly what it should have been. Distrust the data. Check the instruments. Rule out calibration errors, systematic biases, software anomalies. When you are working at the frontier of measurement precision, where the signal you are trying to detect is smaller than the potential error in your instruments, the responsible thing to do is to assume the instruments are wrong until you have exhausted every possible explanation for why they might be. The network of facilities responsible for measuring Earth's rotation includes very long baseline interferometry arrays, which use radio telescopes on different continents pointed at quasars billions of light-years away to measure Earth's orientation in space with extraordinary precision. Those quasars are so distant that they appear fixed against the background of the universe, making them a perfect reference frame for detecting any change in the planet's behavior. Cross-referencing data from these facilities, operated by different institutions in different countries on different continents, produced the same result every time. The instruments were fine, the signal was real. What followed was a systematic effort to identify the cause. Scientists subtracted every known contributing factor from the data, one by one. Tidal forcing from the moon, seasonal atmospheric angular momentum shifts, ocean circulation patterns, post-glacial rebound, the slow rising of land that was compressed under ancient ice sheets and is still adjusting thousands of years after those ice sheets retreated. Each known mechanism was quantified and removed from the signal. What remained was not zero. After accounting for everything the models knew about, a residual acceleration persisted. Something beyond the cataloged causes was pushing the planet forward, and the existing framework had no clean explanation for what it was. In science, that situation is called a residual, a measurement that does not fit the model. And a residual of this size, persisting across multiple years, verified by independent networks on multiple continents, is not something researchers file away and revisit later. It is the most interesting thing in the room. Because a residual means the model is incomplete. It means reality is doing something the theory has not yet accounted for. And the history of physics is littered with examples of residuals that turned out to be the doorway to something fundamental. The deeper researchers dug into what might explain the leftover signal, the more the investigation pulled them in a direction that surprised even those running it. The expected answers, The atmospheric explanation, the ocean explanation, the ice redistribution explanation were all real contributors. But none of them, individually or in combination, fully closed the gap. The residual kept pointing somewhere else, somewhere that instruments could not directly reach, somewhere that no probe had ever survived long enough to explore, somewhere that existed only in seismic data and magnetic field measurements and the slow, patient work of scientists trying to infer the behavior of a place from the ripples it sent upward through thousands of miles of rock. The answer was pointing down, and not just a little down, not into the crust, not into the upper mantle, not into any layer of Earth that geologists have meaningful direct access to. The signal was pointing to the deepest place on the planet, a region that begins nearly 1,800 miles beneath your feet and extends another 1,400 miles further inward. A region that no instrument has ever physically reached and no material we know of could survive in even briefly. A region where iron exists in a liquid state at temperatures hotter than the surface of the star this planet orbits, moving in massive convective currents that generate the magnetic field surrounding everything above them. The outer core. And within the outer core, suspended at the absolute center of everything, wrapped in liquid iron on all sides, rotating in its own private rhythm with no rigid connection to any layer above it, a sphere of solid iron roughly as wide as the moon. The inner core. And the inner core, according to the data, had done something that no model in the 20th century predicted it would do. It had slowed down. It had matched the rotation of the mantle above it for the first time in decades. And then, according to the most recent analysis, it had kept slowing, passing through zero relative velocity and continuing in the other direction. The solid iron center of Earth had reversed its rotation relative to the planet surrounding it. That discovery did not make headlines when it first appeared in the scientific literature. It is the kind of finding that takes time to absorb even for the specialists in the field, because the implications of it, the physical story of what happens when angular momentum begins transferring upward through the layers as a result of a core behavioral change, that story takes years to verify and decades to fully express at the surface. But the timeline fits. The inner core's apparent deceleration in the late 2000s and early 2010s aligns, with a delay appropriate to the coupling timescales between the layers, with the surface acceleration that became measurable starting around 2016. The delay is itself scientifically important. It suggests that information from the center of the planet takes years to decades to propagate upward, which means what the surface is doing right now may not reflect what the core is doing right now. It may reflect what the core was doing 10 or 15 years ago, and whatever the core has done since then has not yet arrived. There is a term in physics for a system in which a change in one part propagates outward and reaches the observer only after a significant delay. It is called a causal lag. And the uncomfortable implication of a causal lag in a system this large is that by the time you can fully measure the effect at the surface, the cause has long since moved on to something else. You are always, in a sense, reading yesterday's news from the center of your own planet. The core sends a message. The message travels upward through thousands of miles of liquid iron and solid rock and slow-flowing mantle, and when it finally arrives at your feet, it carries the echo of a decision the core made years before you were aware anything had changed. The atomic clock caught that echo. A 1.59 millisecond shortening of a June day in 2022 was not random noise. It was a message encoded in the rotation of a planet, sent from the iron interior of the world and received by instruments that had only existed for a few decades and were precise enough to hear it. The clocks cannot lie, and what they are saying, in the patient language of cesium oscillations and quasar interferometry and satellite-measured ice mass, is that something deep inside this planet changed its behavior within the last generation. The surface is still catching up to what happened below, and the systems built on the assumption that the surface would remain predictable are beginning to feel the gap between what was promised and what the planet is actually delivering. How large that gap becomes and how fast it grows depends on forces that have been building since long before anyone thought to measure them. The ice at the poles knew something was changing. The ocean circulation knew. the magnetic field weakening over the South Atlantic in ways that have been accelerating for decades, new. Each of them has been telling the same story in a different language, and each of them connects, through physics that is both elegant and merciless, back to the rotation of the planet you are lying on right now. The story moves next to the deepest chapter, to the place where no sunlight has ever reached, where no sound travels, where the pressure is 3 million times what presses against your skin at this moment, and where a sphere of iron the size of the moon is turning in a direction that, until recently, nobody believed it could. Stay with it. Because what happens at the center of this planet does not stay at the center. It always finds its way up. There is a place inside this planet that no human being has ever seen, not through a camera, not through a probe, not through any instrument that has ever survived the journey far enough to send back a direct reading. We know it exists because of shadows, because of the way sound moves through rock, because of the way a magnetic field bends around something massive and electrically active deep in the interior. We know it the way you might know a fire burning in a sealed room by feeling the heat through the wall. You cannot see the flame, but you can feel what it is doing. And what it is doing right now, in the complete darkness at the center of everything you have ever stood on, is changing. To get there in your mind, you have to descend. Start at the surface. The ground beneath your feet, whether it is soil or concrete or ocean floor, is the outermost layer of Earth's crust. This layer is thin by planetary standards, ranging from about 3 miles thick under the deep ocean to roughly 40 miles thick under the continents. Below it is the mantle, a vast region of rock that under ordinary circumstances appears solid, but over geological timescales flows like an extraordinarily thick fluid, carrying heat from the interior outward, in slow convective cycles that drive the movement of tectonic plates above. The mantle extends nearly 1,800 miles downward. Descending through it, you pass through regions where the pressure transforms the crystal structure of minerals into forms that do not exist at the surface, where rock behaves in ways that would be unrecognizable to any geologist working in a surface laboratory. At the base of the mantle, something changes completely. The rock ends. What begins below is not rock at all. It is liquid metal. The outer core is composed primarily of iron and nickel in a liquid state, beginning roughly 1,800 miles beneath the surface and extending another 1,400 miles further inward. The temperature at the top of the outer core is estimated at around 7,000 degrees Fahrenheit. At the boundary with the inner core below, it approaches 9,000 degrees, comparable to the outer surface of the star this planet orbits. Under those conditions, iron should be a gas. The pressure at that depth is so extreme, so far beyond anything that exists naturally at the surface, that it forces the iron into liquid rather than vapor and keeps it there regardless of the temperature. It is a state of matter that has no analog in ordinary experience, not liquid the way water is liquid, not even liquid the way molten steel is liquid in a foundry, liquid in a way that only exists deep inside large rocky planets, under pressures that would reduce any known material to a crushed, unrecognizable state in an instant. And this liquid is moving. The outer core is not a still pool. It is a churning, turbulent, convecting ocean of electrically conductive metal, driven by the temperature difference between the relatively cooler base of the mantle above and the intensely hot, solid inner core below. Heat rises. The hotter liquid iron near the inner core boundary rises upward through the outer core. As it rises and cools slightly, it sinks again. These convective columns rise and fall in massive rotating structures, shaped and directed by the rotation of the planet above them, influenced by the Coriolis effect, the same force that spins hurricanes and ocean gyres at the surface, but operating at a scale and intensity that dwarfs anything visible from the outside. Those moving columns of electrically conductive fluid generate something extraordinary. Moving electrical charge generates a magnetic field. The convecting iron in the outer core is effectively an enormous self-sustaining electrical generator, wrapping the planet in a magnetic field that extends from the core outward through the mantle, through the crust, through the atmosphere, and out into space for tens of thousands of miles. This is the geodynamo. It is the reason compasses point north. It is the reason migratory birds can navigate by sensing the field's direction and intensity. It is the reason charged particles streaming outward from the sun at millions of miles per hour are deflected away rather than stripping the atmosphere bare and scattering organic chemistry across the vacuum of space. The liquid outer core is, in a direct and non-metaphorical sense, the reason life exists on this planet. It is the engine of the shield that makes everything above it possible. But there is something it does beyond generating the magnetic field, something more immediate to the story of the accelerating rotation, something that connects the boiling darkness 2,000 miles below your feet to the satellites positioning your aircraft and the atomic clocks drifting out of sync with the ground beneath them. The outer core does not rotate at exactly the same rate as the mantle and crust above it. This is a subtle point, but it carries enormous physical consequences. The outer core is a fluid. It is not rigidly attached to the solid rock above. There is coupling between the two layers, transmitted through pressure at their shared boundary and through electromagnetic forces between the electrically active fluid and the lower mantle. But the coupling is not perfect. The core has some rotational independence from everything above it. It can speed up or slow down relative to the surface, within limits, without immediately dragging the surface along with it. When the large-scale circulation patterns inside the outer core shift, when the massive convective columns reorganize and the dominant flow structures change direction or intensity, the torque they exert on the mantle above changes. And changes in that torque propagate upward through the mantle to the crust, producing changes in the rotation rate that show up, years to decades later, in the data collected by radio telescopes pointed at distant quasars. Researchers studying the relationship between changes in Earth's magnetic field and changes in rotation rate have found a pattern that is difficult to dismiss as coincidence. When the field fluctuates in certain characteristic ways, reflecting reorganizations in the outer core circulation, the rotation rate tends to shift correspondingly, with a lag that reflects the time required for angular momentum to transfer upward through the layers. The correlation is strong enough that geophysicists now treat core dynamics as a primary driver of decade-scale rotation variations. Not the only driver, but a primary one. And the outer core's circulation pattern has changed. Satellite magnetic data, particularly the detailed maps produced by the European Space Agency's Swarm constellation, 3 satellites flying in coordinated formation and mapping the magnetic field from orbit with a resolution no ground network could match, show clear evidence of a reorganization in the outer core flow structure beginning in the early years of this century. The change is visible in the behavior of the magnetic field above it. Certain features of the field have shifted. Others have strengthened or weakened in ways that correspond to altered circulation patterns below. The outer core is not doing what it was doing 20 years ago. But to understand why that matters to the rotation of the surface, you need to go deeper still. Because the outer core does not churn in empty space. It wraps around something. Something that sits at the absolute geometric center of the planet. Something solid. Something rotating on its own schedule. Something that, based on the best available seismic data, recently did something that has no precedent in the modern scientific record. At the center of the outer core, suspended in liquid iron on all sides, is the inner core. It begins at a depth of roughly 3,200 miles. It is a sphere of solid iron and nickel approximately 1,500 miles in diameter, roughly the same width as the moon. And it is solid for a reason that is almost paradoxical. At that depth, the temperature is around 9,000 degrees Fahrenheit. Iron at 9,000 degrees under normal circumstances is not solid. It is not even liquid. It is a plasma. But the circumstances at the center of this planet are not normal. The pressure there exceeds 3 million times atmospheric pressure. That weight, the cumulative gravitational compression of the entire planet pressing inward from all directions, forces the iron into a crystalline structure so tightly packed that thermal energy cannot shake it apart. The heat is there. The heat is extraordinary. But the pressure will not let the structure collapse into liquid. The result is a ball of solid iron floating inside a liquid iron ocean, inside a solid rock planet, rotating in its own private rhythm, because the inner core is not rigidly connected to anything above it. The liquid outer core provides the only medium through which forces can be transmitted between the innermost sphere and the mantle and crust above. That liquid coupling is real, but it is not rigid, which means the inner core can rotate at a different rate from the layers surrounding it. For decades, geophysicists suspected it did. The evidence came from the only window we have into the deep interior: earthquakes. When a major earthquake strikes, it sends seismic waves radiating outward in every direction, including straight down through the core and up the other side of the planet. These waves travel at speeds that depend on the material they pass through. The inner core, with its iron crystal structure aligned in a specific orientation, transmits waves slightly faster along certain paths than others. By analyzing recordings of similar earthquakes at the same seismograph stations over multiple decades, researchers found that the wave travel times were changing. The waves were arriving at slightly different intervals than they had in earlier decades. The most straightforward explanation was that the inner core was rotating, slowly turning relative to the surface and changing the orientation of its crystal structure relative to the paths the seismic waves traveled. For years, the scientific consensus was that the inner core was rotating slightly faster than the mantle above it, confirmed by multiple independent analyses, consistent with models of how electromagnetic forces from the outer core would drive the inner core forward. Settled science, or as settled as anything about the deep interior ever gets. Then in 2023, a study published in the journal Nature Geoscience drew a different conclusion from a longer and more complete dataset. The inner core had indeed been rotating faster than the surface through the 1990s. But the data showed that sometime around 2009, that over-rotation had slowed. The inner core matched the mantle above it for a period, and then, according to the analysis, it kept decelerating, past zero relative velocity, into negative territory. The solid iron center of Earth was now rotating fractionally slower than the mantle and crust surrounding it. Relative to the surface, it had reversed direction. Sit with that for a moment. The innermost object on this planet, a sphere of solid iron the size of the moon, turning in the total darkness at the center of everything, is now spinning in the opposite direction relative to the ground you are standing on. The forces involved in that reversal are not small. The angular momentum of the inner core is an enormous quantity. When it decelerates, that angular momentum does not vanish. Angular momentum is conserved. It transfers outward, through the liquid outer core, to the mantle, to the crust, to the surface. A decelerating inner core is effectively donating its rotational energy upward through the layers. The surface receives that energy as an increase in its own rotation rate. It spins up. The days get shorter. The timeline of the inner core deceleration, centered on the years 2009 to 2012, aligns with a lag of several years with the surface acceleration that became clearly measurable from 2016 onward. The lag is physically expected. Angular momentum does not transfer instantaneously through thousands of miles of liquid iron and solid rock. It propagates. It takes time. And the fact that the surface started accelerating years after the core started decelerating, with an interval that matches theoretical estimates of the coupling timescale between these layers, is the kind of alignment that makes researchers lean forward in their chairs. It is not proof. Science does not work on alignment alone. The inner core reversal is contested. There are credible researchers who argue that alternative explanations exist for the seismic data, that the inner core surface may have topographic features that scatter waves differently over time without requiring rotation, that changes in the outer core above could affect wave travel times independently of anything happening in the solid sphere below. The debate is genuine, and the data required to settle it definitively does not yet exist. But here is what both sides agree on. Something changed in the deep interior of this planet in the years around 2009 to 2012. The seismic signature of the inner core behaves differently now than it did in the 20th century, and whatever changed down there is connected, through physics that is well understood, even if the specific details remain debated, to what the surface is doing now. The iron heart of this planet shifted. The echo is still traveling upward, and by the time it reaches the surface completely, the center may have already moved on to something new, something we cannot yet detect because the message has not arrived. That is what it means to live on a layered world. You are always receiving news from the interior on a delay. The planet is always several years ahead of your ability to read it. And the instruments that caught the missing millisecond, the atomic clocks and radio telescopes and satellite constellations, are the first tools in human history precise enough to hear what the interior is whispering. What they are hearing right now is not alarming in the way a siren is alarming. It is alarming in the way a change in a familiar sound is alarming. When something that has always made one kind of noise begins making another, the right response is not panic. It is attention, careful, patient, rigorous attention. And the next layer of this story demands exactly that. Because while the core drives the planet from the inside, something is happening at the surface that is visible from space, measurable by satellites, and accelerating faster than almost every model from a decade ago predicted. The ice is moving. The weight of the poles is shifting. And when the weight of a spinning object shifts, the spin itself changes in ways that reach all the way down to the decisions engineers are making right now about the systems your life depends on. If you have stayed this far, you already understand that this story is not about a number on a scientific instrument. It is about the planet you live on telling you, in the only language it has, that something fundamental is in motion. The question is whether anyone is listening closely enough to understand what comes next. Keep listening. Because what the ice is doing at the poles, what it is doing to the axis of rotation itself, to the geographic location of north, to the moment of inertia of a planet 4.5 billion years old, that is where this story becomes something you can see from space. And it is more unsettling than the iron. There is a demonstration that physics teachers have used for decades to make an abstract principle suddenly, viscerally real. A person sits on a rotating stool. In each hand, they hold a weight. Arms extended outward, the stool spins at a slow, lazy rate. Then they pull their arms inward, drawing the weights close to their chest, close to the axis of rotation. And the stool accelerates, dramatically, without anyone pushing it, without any new energy being added to the system. The person simply moved mass closer to the center, and the rotation responded, as if something invisible had reached down and spun the stool harder. Every student who sees it for the first time has the same reaction. It feels like a trick. It feels like something was added that should not have been there. But nothing was added. The physics is conservation of angular momentum, one of the most fundamental principles in the universe, operating exactly as it always does. Move mass inward toward a rotation axis, and the rotation speeds up. Move mass outward away from the axis, and the rotation slows. The total angular momentum of the system stays constant. The distribution of it changes, and the spin rate adjusts accordingly, with a precision that is almost eerie in how reliably it behaves. Now scale that demonstration up by a factor that is difficult to hold in the mind. For most of the last 20,000 years, enormous quantities of mass were locked near the poles of this planet in the form of ice sheets. The polar regions sit close to Earth's rotation axis, the imaginary line running through the geographic north and south poles around which everything else turns. Ice concentrated near the poles is mass concentrated near the axis, and for tens of thousands of years that configuration held. The great ice sheets of the last glacial maximum covered large portions of North America, northern Europe, and Antarctica in layers of ice that in places reached 2 miles thick. Millions of cubic miles of frozen water, sitting close to the rotation axis, keeping the angular momentum distributed in a particular way, contributing to a rotation rate that human civilization grew up inside. Then the ice began to melt. Gradually at first, driven by natural orbital cycles. The great deglaciation that began roughly 15,000 years ago redistributed enormous quantities of water from the poles into the ocean basins, moving mass away from the rotation axis, increasing Earth's moment of inertia and contributing to a gradual slowing of the rotation rate. That effect is still operating today. The land beneath the former ice sheets of North America and Scandinavia is still rising, slowly rebounding upward as it recovers from the weight of ice removed thousands of years ago. That rebound is itself redistributing mass, pulling material back toward the poles, and subtly working against the rotation acceleration. For most of the Holocene, the long stable period of warmth and relatively predictable climate that human civilization was built inside, these processes were slow, gradual, operating on timescales of centuries and millennia. They were part of the background behavior of the planet, the slow, rhythmic breathing of a world adjusting itself across geological time. Then something changed in the rate. The Greenland ice sheet is the largest body of ice in the northern hemisphere. It covers an area roughly 3 times the size of Texas and contains enough frozen water that if it melted entirely, global sea levels would rise by roughly 23 feet. For most of recorded history, it was gaining and losing mass in rough seasonal balance. In winter, snowfall added mass. In summer, surface melt removed it. The net annual change was small enough to be within the natural variability of the system. That balance has broken. Since the 1990s, Greenland has been losing mass at an accelerating rate. In the early years of the acceleration, the loss was measurable but modest. By the 2000s, it had climbed to roughly 200 billion metric tons per year. By the most recent measurements, it sits at approximately 280 billion metric tons of ice lost every single year. That number requires a moment to translate into physical intuition. 280 billion metric tons is roughly equivalent to the combined weight of every human being who has ever lived, multiplied by a substantial factor, vanishing from the polar region and entering the ocean every 12 months. And Greenland is not alone. The West Antarctic ice sheet, the portion of Antarctica's ice that sits on rock lying below sea level and is therefore particularly vulnerable to warming ocean water intruding beneath it, is losing approximately 150 billion metric tons per year. Together, the two ice sheets are removing more than 400 billion metric tons of mass from the polar regions annually. That mass is not disappearing. It is flowing into the ocean basins, redistributing itself across lower latitudes, moving away from the rotation axis. We know this with extraordinary precision because we have been watching it from space. The Gravity Recovery and Climate Experiment, known as GRACE, and its successor GRACE Follow-On, represent one of the most elegant measurement concepts ever put into orbit. 2 satellites fly in formation approximately 130 miles apart, tracing the same orbital path one behind the other. Between them, they continuously measure the distance separating them to within a fraction of a micrometer, a fraction of the width of a human hair. When one satellite passes over a region of higher gravitational pull, caused by a concentration of mass below, it is tugged forward slightly, increasing the gap between the 2 satellites by a tiny amount. When the trailing satellite reaches the same region, it accelerates and closes the gap. By tracking the continuously changing distance between the 2 satellites, scientists can map variations in Earth's gravitational field across the entire planet, updating the map with each orbital pass. Mass that moves leaves a gravitational signature. Ice that melts and flows into the ocean reduces the gravitational pull over the poles and increases it over the ocean basins. GRACE has been reading that signature continuously since 2002, producing the most detailed and comprehensive record of planetary mass redistribution ever assembled. The picture it reveals is stark. The poles are losing mass. The mid-latitude ocean basins are gaining it. The redistribution is happening in real time at rates that have been accelerating year over year, and the gravitational maps produced by the satellites update regularly to reflect a planet that is genuinely, measurably different from what it was when the mission began. That redistribution carries a rotational consequence that follows directly from the same physics governing the spinning stool. Mass moving away from the poles and settling into lower latitude ocean basins is mass moving away from the rotation axis. An increased distance of mass from the rotation axis means an increased moment of inertia. With angular momentum conserved, an increased moment of inertia means a decreased rotation rate. The ice loss is, in the long term, a force pushing toward a slower spin, the planet pulling its arms outward. But here is the complication that makes the short-term picture far more complex than the long-term trend would suggest. The redistribution is not happening uniformly. Different portions of the ice sheets are melting at different rates. Different ocean basins are receiving the meltwater at different depths and different latitudes. The three-dimensional geometry of where mass is going and how that interacts with Earth's irregular shape produces effects that do not resolve simply into a slower spin. They produce a rotating shift in the direction of the axis itself. The geographic North Pole, the point on the surface directly above Earth's rotation axis, is moving. This is not a statement about the magnetic North Pole, which has been known to wander for decades and which has been drifting notably in recent years. This is the actual rotation axis, the physical line around which the planet spins. It has shifted. Not dramatically, not in any way that would be apparent to casual observation, but measurably, detectably, by amounts that matter enormously to the precision systems that depend on knowing exactly where the axis is. For most of the 20th century, the geographic North Pole drifted slowly in one direction toward northern Canada at a rate of a few centimeters per year. The cause was post-glacial rebound, the continuing adjustment of the crust and mantle to the removal of the Great Laurentide ice sheet that covered North America during the last glacial maximum. That rebound pulls mass back toward the poles, tugging the axis in its direction. Then around the year 2000, something changed. The direction of the drift reversed. The pole turned eastward, toward Greenland, and the rate increased substantially, from a few centimeters per year to roughly 17 centimeters per year across the 2000s and 2010s. The jump in both direction and speed is striking enough to demand an explanation. When researchers analyzed the GRACE satellite data to identify the cause, the answer came back clearly. The primary driver was accelerated ice loss from Greenland. Greenland sits in a specific geometric relationship to the polar drift trajectory. As its ice sheet sheds mass, it alters the distribution of planetary mass in a way that pulls the rotation axis in a new direction. The correspondence between the onset of accelerated Greenland mass loss and the shift in polar drift direction is precise enough that scientists treat them as directly linked. The pole is following the ice. As the ice moves, as its distribution across Greenland shifts with seasonal melt patterns and glacier retreat, the axis follows behind it like a compass needle slowly responding to a changing field. The West Antarctic ice sheet contributes its own pull, adding a component that amplifies the eastward trend. And both contributions are growing because the ice loss in both regions is accelerating. What this means practically is that the actual geographic location of the North Pole is now measurably different from where it was when most of the infrastructure of modern civilization was designed. Not by a large amount, not by anything visible to the naked eye, but every system that uses the precise location of Earth's rotation axis in its calculations, satellite navigation systems, geodetic survey networks, the reference frames used for everything from mapping to orbital mechanics to timekeeping, all of them must be continuously updated to account for a pole that will not stay where the previous generation of engineers assumed it would. The International Earth Rotation and Reference System Service, based in Paris, publishes updated Earth orientation parameters every few days. Those parameters feed directly into the correction models used by satellite navigation systems worldwide. The update frequency has increased in recent years. The corrections being applied have grown larger. The rate of change is outpacing what earlier models projected. And there is a second-order effect that sits underneath all of this, quieter and stranger than the axis drift itself. The mass redistribution from ice loss does not just shift the axis. It changes how the planet responds to other forces acting on it. It alters the coupling between the fluid layers and the solid layers. It changes the resonance frequencies of the wobbles that Earth naturally develops as a non-spherical spinning body. And one of those wobbles, a rhythmic rocking of the rotation axis relative to the solid body of the planet, operating on a cycle of roughly 14 months, began behaving in a way that stopped researchers mid-sentence when they noticed it. The wobble nearly stopped. The Chandler wobble is one of the most reliable features of Earth's rotational behavior. Named for the American astronomer who documented it in the 1890s, it traces a small circle roughly 30 feet across at the pole, repeating on its 14-month cycle, driven by the geometry of a planet that is not quite spherical. It has been operating continuously and predictably for as long as it has been measured. Then around the year 2000, its amplitude began to decrease. By roughly 2005 to 2006, the wobble had dropped to approximately 1/5 of its typical size. It had very nearly disappeared. The leading explanation involves a redistribution of pressure on the deep ocean floor, driven by changes in ocean circulation, a reorganization of where cold, dense water sinks to the bottom of the ocean basins. that happened to damp out the excitation keeping the wobble going. The wobble eventually recovered. By the late 2000s, it was closer to its normal amplitude, but the episode revealed something uncomfortable. A feature as fundamental and geometrically determined as the Chandler wobble, operating reliably for as long as the modern record exists, could be significantly suppressed by changes in ocean circulation. If ocean changes could do that, other changes could alter other fundamental rotational features. And the ocean is not the only thing changing. The ice loss continues. The axis continues to drift. The moment of inertia continues to shift. And each year of additional ice loss adds to the cumulative displacement, compounding in a direction that the planet has not experienced at this rate in at least 10,000 years, the entire span of human civilization. The infrastructure built across those 10,000 years was calibrated to a world in rotational equilibrium. It assumed the poles would remain in a predictable location. It assumed the axis would drift within the narrow range that the instrumental record had established as normal. That assumption is now being revised, not catastrophically, not all at once, but consistently, in one direction, with no indication that the forcing is about to reverse. The ice has been accumulating at the poles for millions of years. It is leaving in decades. And the planet is responding to that departure the way any spinning system responds to a redistribution of its mass. It shifts, it adjusts, it finds a new balance point. And everything built on the assumption of the old balance point, the clocks, the satellites, the navigation systems, the grids, all of it has to be recalibrated to find the new one. But the ice and the axis drift are only part of the picture. There is a layer of the story that most people outside the engineering community have never encountered. A layer that turns the abstract physics of rotation into something immediate, something that touches every digital transaction and every powered device and every navigation-dependent system on the planet. A layer that forced the largest technology companies on Earth to develop their own private workarounds to a problem they could not solve by waiting for someone else to fix it. It involves a single second. A second that, if removed from the official record without warning, the engineers who have studied it say, could be one of the most disruptive events in the history of global digital infrastructure. A second that cannot exist without breaking things. And a second that the accelerating planet may eventually force into existence, whether the infrastructure is ready for it or not. In 1972, the world made a quiet agreement. Not a treaty, not a declaration. Just a technical decision made by a committee of scientists and engineers in a room that most people alive at the time had never heard of, about a problem most people alive at the time did not know existed. The decision seemed small, a patch, a correction mechanism for a gap that was opening slowly between two different ways of measuring time. Nobody in that room predicted that 50 years later, the largest technology companies on Earth would be publishing internal engineering papers about it. Nobody predicted that it would become one of the most debated topics in the infrastructure community. Nobody predicted that the planet itself would eventually force a reckoning that the patch was never designed to handle. The problem the 1972 decision was trying to solve was this. Atomic clocks measure time by counting the vibrations of cesium atoms. They do not care about the planet. They do not drift. They do not fluctuate with the seasons or respond to changes in ocean circulation or adjust when the inner core shifts its rotation. They simply count, perfectly, relentlessly, without reference to anything outside the atom itself. And Earth's rotation, measured against those clocks, is imperfect. It fluctuates, it drifts, it speeds up in some years and slows in others. It is, by the standards of cesium atoms, an unreliable timekeeper. For most of human history, that did not matter. Time was defined by the planet. A day was the time it took the sun to return to the same position in the sky. A second was a fraction of that. The imperfections of the planetary clock were baked into the system because there was no alternative reference. Then atomic clocks arrived, and for the first time there was a reference more reliable than the planet. And the planet, measured against that reference, kept falling out of alignment. If nothing was done, atomic time and Earth time would drift further apart with every passing year. Noon on the atomic clock would eventually arrive while the sky still showed late morning, not next week, not next decade. Across centuries, the drift would accumulate into something undeniable. The sun would disagree with the clock. And every system built on the assumption that the clock and the sun agreed would begin to fail in ways that were difficult to diagnose because the disagreement was so slow and so gradual. The solution was the leap second, a simple, surgical intervention. Once or twice a year, when the accumulated gap between atomic time and Earth time grew large enough, international timekeeping authorities would add a single extra second to the official clock. At 23 hours, 59 minutes, and 59 seconds, instead of rolling forward to midnight, the clock would tick to 23 hours, 59 minutes, and 60 seconds. One extra heartbeat. One manufactured moment inserted into the flow of global time to keep the two systems in alignment. 27 leap seconds have been added since the system began. Not one has ever been removed. The logic was always in one direction. Earth was gradually slowing. Atomic clocks were gradually pulling ahead. The correction was always additive, always forward. You added time to the official clock to let the planet catch up. The direction of the adjustment was so consistent, so predictable, that the engineers who built the world's digital infrastructure in the decades following 1972 designed their systems around a simple assumption. Time only moves forward. Clocks only need to be nudged ahead. The second that arrives is always the next one in sequence. That assumption is now in danger. Because the planet is no longer slowing, it is speeding up. Atomic clocks are no longer pulling ahead of Earth time. Earth time is pulling ahead of atomic clocks. And for the first time in the 50-year history of the leap second system, the discussion has shifted from when to add the next second to something that has never been done before in the history of global timekeeping. Whether to remove one, a negative leap second, a moment in time that would not exist. Clocks would tick from 23 hours, 59 minutes, and 58 seconds directly to midnight. 23 hours, 59 minutes, and 59 seconds would simply not occur. That second would be skipped, erased, removed from the record as if it had never been scheduled. The engineers responsible for global internet infrastructure have a specific, considered, and deeply alarmed response to that possibility. In 2022, Meta, the company that operates Facebook and Instagram and the infrastructure connecting billions of devices to those platforms, published a detailed technical paper on the risks of a negative leap second. The language in that paper is notable for its directness. The engineers described a negative leap second as having the potential for a devastating effect on software relying on timers or schedulers. They recommended that one should never be introduced. Their preferred alternative was to allow the gap between atomic time and Earth time to accumulate, gradually smearing any necessary correction across hours rather than applying it in a single jump. Google, Amazon, and Microsoft independently arrived at similar conclusions and developed their own versions of time smearing as a protective measure. The fact that the three largest technology infrastructure companies on Earth each independently decided to engineer around this problem, rather than trust the official correction mechanism, tells you something important about the scale of the risk they assessed. To understand why a single removed second is so dangerous, you need to understand what the internet assumes about time. The network time protocol is the system that keeps clocks synchronized across billions of devices worldwide. It runs constantly in the background, making tiny adjustments to keep every server, every router, every network device operating in the same version of time. It was designed with one fundamental assumption, embedded so deeply into its architecture that changing it would require rebuilding large portions of the system from the ground up. The assumption is that time moves forward. Always. Without exception. A timestamp on a piece of data is always later than the timestamp on the data that came before it. The sequence of events is always the sequence of timestamps. When a negative leap second removes 23:59:59 from existence, that assumption breaks. Devices that implemented the correction properly will jump directly from 58 seconds to midnight. Devices that did not, or that implemented it differently, will briefly disagree about what time it is. For the duration of that disagreement, some devices will believe they are 1 second ahead of others. And in a system where the sequence of timestamps determines the sequence of events, a 1-second disagreement is not a cosmetic problem. It is a causality problem. Processes scheduled to run at a specific timestamp can trigger twice on systems that handle the correction differently from the systems they are communicating with. Log files that record events in chronological order can record a new event as occurring before an old one, because the new event's timestamp falls in the second that was supposed to have been removed, and different systems disagree about whether that second exists. Security certificates that verify identity by comparing timestamps against an expected range can fail, because the timestamp on the certificate falls in a moment that one system says occurred and another system says never happened. In financial markets, the consequences become quantifiable in ways that make the technical problem feel very concrete. High-frequency trading systems execute thousands of transactions per second. The matching of buyers and sellers in an order book depends on the precise sequence of submitted orders. If one exchange's clock jumps backward while another's does not, the sequence of trades becomes ambiguous. A trade placed after the removed second might be logged as having occurred before a trade placed before it. Regulatory requirements in multiple jurisdictions demand timestamp accuracy to the microsecond for transaction records. A 1-second reversal does not create confusion. It creates legal liability. Trades that appeared settled become disputed. The volume of reconciliation discrepancies that a negative leap second would generate in global clearing systems has been modeled by the Bank for International Settlements. The conclusion they reached was significant enough to remain internal. Power grids carry the physical version of the same problem. Alternating current flows at a fixed frequency, 50 or 60 cycles per second depending on the country. Regional grid operators synchronize their networks to a global time standard to balance electrical load across interconnected systems spanning thousands of miles. When the time standard experiences a discontinuity, the synchronization signal contains a glitch. In most cases, automatic protective systems compensate quickly, but there is a window, brief but real, during which the coordination signal is ambiguous. Grid engineers have a term for what can happen in that window: a synchronization event. And synchronization events, even brief ones, are the precursor to the kind of cascading failures that bring down large sections of a grid. Aviation adds another layer. Modern instrument approaches at airports use satellite positioning to guide aircraft to within feet of a runway in conditions where pilots cannot see the ground until they are 100 feet above it. The tolerances on these approaches are measured in meters laterally and feet vertically. The systems delivering that precision depend on synchronized timestamps across satellite constellations, ground control networks, and onboard avionics. A 1-second discontinuity propagating through that chain does not just affect the numbers, it affects the integrity of the position fix at the exact moment when precision matters most. And hospitals. Modern hospitals are dense with time-critical systems. Medication dispensing logs, timestamps on every dose administered. Operating room equipment records data against synchronized timestamps that form the legal medical record. Radiological systems that deliver cancer treatment use precise timing to coordinate beam delivery with a patient's breathing cycle. A 1-second gap in the timekeeping record does not simply create a data anomaly in these systems. It triggers automatic safety alerts. In some cases, it initiates automatic shutdowns pending manual verification. A hospital that loses confidence in its timing infrastructure, even briefly, even for a single second, is a hospital that pauses to check. And in a surgical suite, a pause to check is not an abstract engineering event. It is a human event. In 2022, an international standards body voted to eliminate the leap second entirely by 2035. The decision was framed as a solution. Remove the mechanism that creates the risk. Stop adding or removing seconds. Let atomic time and Earth time diverge without correction until a different mechanism, designed for larger adjustments applied over longer periods, can handle the accumulated gap. But the decision does not eliminate the problem. It defers it. The gap between atomic time and Earth time will continue to grow. The policy allows it to grow to a maximum of 1 minute before intervention is required. At the current rate of Earth's acceleration, reaching 1 minute of accumulated drift would take roughly a century. That sounds like a comfortable margin. Except the current rate is not a reliable guide to the future. If the acceleration continues, the gap grows faster. If a reversal occurs and the planet slows dramatically after years of speeding up, the gap grows even faster in the opposite direction. And the infrastructure systems being built today, The satellite constellations, the power grid control systems, the financial clearing networks are designed with operational lifetimes of 20 to 30 years. The engineers specifying those systems right now have to make assumptions about what the timekeeping environment will look like in 2045 and 2050. And the planet, by behaving in ways the models did not predict, is making those assumptions harder to defend. There is something profound and slightly vertiginous about this situation when you step back from the engineering details and look at the shape of it. Human civilization built an entire global infrastructure on the assumption that the planet beneath it was predictable. Not perfectly predictable, not static, but predictable within a range that could be managed with periodic small corrections. And for 50 years, that assumption held. The leap second was adequate. The corrections were manageable. The clock and the planet stayed close enough that the gap between them never threatened anything fundamental. Now the planet is moving outside the range the system was designed for. Not catastrophically, not all at once, but consistently and in a direction that was not anticipated, and that the existing correction mechanism was not designed to handle. The second that cannot exist, the 235959 that may one day be removed from global time, is a symptom of that movement. It is the place where the abstract physics of a spinning planet becomes a concrete engineering crisis with real consequences for real systems that real people depend on. And the deeper you look into why the planet is behaving this way, the more you find that the second is not the story. The second is just the most visible surface of a much larger and much stranger truth about what is happening inside and around the world you are living on. The rotation, the ice, the core, the magnetic field, the axis, all of it is connected. All of it is in motion. And the motion is not random. It is following a pattern. And that pattern, when you look at it across all the systems simultaneously, points towards something that researchers in multiple independent fields have each arrived at separately, from different directions, using different instruments and different methods, something that the ancient rocks already knew, something written in the seafloor and the coral and the ice cores and the frozen magnetic minerals of volcanic basalt laid down in ages, when the only witnesses were the planet itself and the star above it. This is the channel where the universe keeps no secrets. If you have been here from the beginning of this story, you already know that what lies ahead reaches further than a millisecond and deeper than any clock. Follow nocturnal space. Stay close. Because the next layer of this story is the one that changes how you see everything above you when you look at the night sky. The magnetic field is speaking. And what it is saying about where this planet has been and where it may be going is the kind of thing that makes even the scientists who study it pause before they answer. There is something surrounding this planet right now that you cannot see, cannot feel, and cannot measure with any instrument available to ordinary life. It has no color. It has no sound. It does not interact with light in any way that would make it visible to the human eye. And yet, without it, you would not be here. Nothing would be here. Not the atmosphere you are breathing. Not the water in the oceans. Not the complex chemistry that assembled itself into living organisms across hundreds of millions of years of patient iteration. Without this invisible structure wrapping the planet, the star above would have stripped everything away long ago, and Earth would be a dry, irradiated rock indistinguishable from 100 other barren worlds in this solar system. The magnetic field is not decoration. It is the precondition for everything. It works like this. The sun is not a quiet object. It is a nuclear furnace radiating energy in every direction simultaneously, and a significant portion of that energy comes not as light but as charged particles. Protons, electrons, helium nuclei stripped of their electrons and accelerated outward at hundreds of miles per second in a continuous stream called the solar wind. When that stream encounters a planet with no magnetic field, it does not slow down politely. It interacts directly with the upper atmosphere, gradually stripping away lighter molecules, ionizing gases, and over geological timescales, eroding the atmospheric envelope that makes liquid water and biological chemistry possible. Mars is the most instructive example in our solar system. Mars lost its magnetic field billions of years ago when its core cooled and the geodynamo that generated it shut down. What followed was the slow, inexorable loss of most of its atmosphere. What was once, according to the geological evidence, a world with liquid water on its surface became a cold, thin-aired desert, where the atmospheric pressure at the surface is less than 1% of what you experience right now. Earth did not follow that path. Earth retained its magnetic field because its interior stayed hot enough and its outer core stayed liquid enough to keep the geodynamo running. The field deflects the solar wind. It creates a bubble of protected space around the planet called the magnetosphere, inside which the atmosphere is shielded from the most energetic particle bombardment the sun produces. The field is not impenetrable. Charged particles find their way in at the poles, spiraling down magnetic field lines and producing the auroras that light up high-latitude skies. But the auroras are the exception, the small fraction of particle energy that gets through at the specific geometric weak points of the system. The vast majority is deflected. That deflection is what makes this planet livable, and the field generating that deflection is weakening. Not everywhere, not uniformly, not in a sudden dramatic way that would register in your daily experience, but measurably, consistently, in a pattern that has been building for centuries, and that the most precise satellite measurements ever made have now documented in enough detail to produce something approaching genuine scientific alarm. The global average intensity of Earth's magnetic field has declined by roughly 9% since systematic measurements began in the early 19th century. 9% in approximately 180 years. That rate of decline, if it continued linearly, would not produce a catastrophically weak field for many centuries. But the decline is not uniform across the planet, and in one specific region, the weakening has been happening faster, deeper, and with a structural character that researchers have been watching with increasing unease for decades. The South Atlantic anomaly. It sits over the South Atlantic Ocean and extends across much of South America. It is a region where Earth's magnetic field is dramatically weaker than it should be at those latitudes. At the center of the anomaly, the field intensity is roughly 40% weaker than the global average for equivalent latitudes elsewhere on the planet. That number is not a small regional variation. It is a profound structural absence in the planetary shield, a thinning in the armor at a specific geographic location, and everything passing through that location from above encounters significantly less protection than it would anywhere else on Earth's surface. The consequences are most visible at altitude. Satellites in low Earth orbit pass through the South Atlantic anomaly on a regular basis depending on their orbital inclination. And when they do, they encounter elevated levels of energetic charged particle radiation. The effect on electronics is well documented. Energetic particles passing through semiconductor components can flip individual bits in computer memory, converting a 0 to a 1 or a 1 to a 0 in a process called a single event upset. In most cases, these bit flips are caught by error correction systems and corrected before they propagate. In some cases, they are not. Satellites passing through the anomaly experience higher rates of anomalous behavior, unexpected resets, corrupted data, instrument malfunctions, than satellites operating outside it. The engineering community has known about this for decades and designs missions accordingly, adding radiation hardening, implementing more aggressive error correction, planning operational procedures around the increased radiation environment in that region. The International Space Station passes through the anomaly multiple times per day due to its orbital inclination. Astronauts aboard the station are aware of it. Sensitive experiments are managed around the anomaly passes. The radiation exposure the anomaly produces is a known operational consideration for human spaceflight in low Earth orbit, not a theoretical concern, but a daily reality of operating in that environment. None of this is new. The anomaly has been documented since the 1950s. What is new is what the satellite measurements of the past 2 decades have revealed about its trajectory. The anomaly is growing. It is expanding in geographic area, extending its boundaries outward from the original concentrated region over the South Atlantic. It is deepening in its minimum intensity, the weakest point within the anomaly becoming weaker year by year, and it is showing structural signs that researchers find particularly significant. The single minimum that characterized the anomaly for most of the period it has been measured is developing into something more complex. The data shows evidence of a second minimum forming, a split in the anomaly's structure that would produce two distinct weak regions rather than one. If that split develops fully, the geographic footprint of elevated radiation exposure in low Earth orbit will expand substantially, covering a larger swath of the orbital environment that satellites and crewed spacecraft operate within. The cause of the anomaly is rooted in what is happening in the outer core beneath that region. Directly below the South Atlantic, at the boundary between the lower mantle and the outer core, there is an unusual structure. A region where the liquid iron in the outer core behaves differently from the surrounding material, where the flow patterns are distinct, where, according to the best current interpretation of the magnetic field data, there may be a patch of reversed magnetic polarity, a local region where the field alignment is opposite to the dominant global direction. The interaction between this reversed patch and the overall field above it produces a region of field cancellation at the surface. Where the reversed patch pulls against the dominant field, the two partially cancel each other out. The result at the surface and above is a weakened field. The anomaly is the visible symptom of this internal conflict, projected upward from the core boundary through 2,000 miles of mantle to the surface and beyond. The reversed patch is not static. The satellite magnetic data shows it growing. Its boundaries are expanding, its influence on the field above is increasing, and as it grows, the anomaly grows with it. This is where the rotation story and the magnetic field story intersect, in a way that neither field of research can fully address in isolation. The outer core flow patterns that generate the magnetic field are the same flow patterns that interact with the mantle above through electromagnetic coupling and produce torque on the planet's rotation. Changes in the field reflect changes in the flow, and changes in the flow affect the rotational coupling between the core and the surface. The South Atlantic anomaly is not a separate phenomenon from the rotation acceleration. Both are symptoms of the same underlying change in the outer core's behavior. The field and the rotation share an origin. When the origin changes, both change together. The question that this raises, the question that pulls the discussion into territory that is genuinely difficult to communicate without either overstating the uncertainty or understating the significance, is what comes after a weakening field. What does the trajectory of this decline, extended forward through the physics that governs it, eventually produce? The answer written in the rocks is magnetic reversal. Earth's magnetic field has reversed hundreds of times across the planet's history. The evidence is preserved in seafloor basalt. As new oceanic crust forms at mid-ocean ridges, molten rock cools and solidifies, and the magnetic minerals within it freeze in alignment with the ambient field at the moment of cooling. The seafloor spreading away from those ridges in both directions carries a record of the field's polarity at the time each strip of rock solidified. The pattern preserved in the seafloor is a series of alternating stripes, normal polarity and reversed polarity, extending outward from the ridge in a symmetric record of the field's history going back hundreds of millions of years. That record shows that reversals are a normal feature of Earth's behavior. The field has always eventually reversed. The average interval between reversals is roughly 200,000 to 300,000 years, though the actual timing is highly irregular. The shortest documented interval between reversals is tens of thousands of years. The longest documented stable polarity period is tens of millions of years. The last full reversal, called the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. By the average statistics, the current polarity period is overdue for a reversal by several 100,000 years. That statement requires careful handling. Overdue in this context does not mean imminent. The timing of reversals is not governed by a clock. Being past the average interval tells researchers almost nothing about when the next reversal will occur. It could be tomorrow in geological terms, meaning within the next tens of thousands of years. It could be millions of years away. The statistical distribution of reversal intervals is wide enough that any particular interval tells you very little about the next one. What the current data does show is that the field is in a state consistent with the early stages of either a full reversal or what researchers call a geomagnetic excursion. An excursion is a partial reversal, a period where the field weakens significantly and its direction becomes unstable and irregular without completing a full polarity flip, or before recovering and returning to its previous orientation. Excursions have occurred multiple times in the geological record and are generally shorter in duration than full reversals. The most studied excursion, called the Lachamp event, occurred roughly 42,000 years ago. During that event, field intensity dropped dramatically over a period of centuries, remained low for several thousand years, then recovered. Evidence preserved in cave deposits, ice cores, on and tree rings from the period of the Lachamp event shows elevated cosmic ray flux reaching the surface during the field minimum. Some researchers have connected the timing to accelerated climate changes and ecological disruptions in the megafauna record of that period, though the causal relationships remain debated. What is not debated is that the reduced field produced measurable effects in the geological and biological record. The atmosphere was affected. The surface radiation environment changed. The consequences were real. A future reversal or excursion would not be identical to the Lachamp event. The details of any future magnetic transition depend on the specific dynamics of the outer core at the time it occurs, and those dynamics are not predictable on the timescales of human planning. But the range of consequences that the geological record associates with magnetic transitions provides a framework for what the systems of the present might face. During a reversal transition, the field does not simply flip instantaneously from one polarity to the other. The transition takes thousands of years. During that period, the field passes through a phase of significantly reduced global intensity, potentially dropping to 10 to 20% of its normal strength. The protection against solar energetic particles is reduced across most of the planet. The increased particle flux reaching the surface would elevate radiation exposure for organisms and electronics alike. Satellite systems operating in the reduced field environment would experience higher rates of the single event upsets that the South Atlantic anomaly already produces locally, but now distributed globally across all orbital inclinations. The engineering margins built into satellite design around the current radiation environment would be insufficient. The effects on biological navigation systems that depend on magnetic sensing would be significant. Migratory birds use the field's direction and intensity to navigate across hemispheres. Sea turtles return to their natal beaches by following magnetic signatures. Certain fish species maintain orientation through magnetic sensing. A field that weakens globally and loses its stable directional structure would disrupt navigation for every species that depends on it. The scale of that disruption across migratory ecosystems is difficult to model, but impossible to dismiss. Power grid infrastructure faces a specific vulnerability that the South Atlantic anomaly already demonstrates in miniature. When energetic charged particles penetrate deeper into the atmosphere during periods of reduced magnetic shielding, they can interact with long conductor lines such as power transmission cables to induce electrical currents. Those induced currents, called geomagnetically induced currents, can damage transformers and other grid components. Large geomagnetic storms already produce this effect occasionally, and several significant grid disruptions in recent history have been traced to geomagnetically induced currents during intense solar activity. A globally weakened field would make this vulnerability chronic rather than occasional. These are not science fiction scenarios. They are the physically expected consequences of a process that the geological record confirms has happened repeatedly. The planet has been through reversals. Life has survived them. But life in past reversals did not depend on a global satellite navigation network, a planetary electrical grid, or a financial system synchronized to microsecond precision across continents. The field that is weakening right now is the same field that was in place when every piece of infrastructure on this planet was designed and built. The tolerances those systems were built to, the radiation environments they were hardened against, the magnetic conditions they were calibrated for, all of it was based on a field operating within the range of the last 10,000 years. If the field moves outside that range, the systems move outside their design envelope. And the field is already moving. The anomaly is already growing. The global intensity is already declining. The inner core, whose behavior couples directly to the outer core dynamics driving both the field and the rotation, has already changed direction. The signals are not subtle anymore. They are in the satellite data. They are in the seismic records. They are in the rotation measurements. They are in the magnetic maps produced by 3 satellites flying in formation above a planet that is quietly, consistently, and in ways that the instrumental record has never captured before, rearranging itself. The ancient rocks knew this was coming. They carry the record of every time it happened before, and what that record shows about the last time multiple systems changed simultaneously, about what the planet looked like the last time the rotation and the field and the ice and the core all shifted together, that is the final chapter of this story. The one that the geological record wrote in basalt and coral and sediment across hundreds of millions of years. The one that puts everything measured in the last decade into a context that is both humbling and clarifying. The planet has a memory. It is longer than civilization, and it has seen this before. There is a library inside this planet, not built by hands, not organized by any intelligence that planned its construction. A library assembled across 4 billion years by the planet itself, pressing its own history into stone, into ice, into the frozen magnetic minerals of cooling basalt, into the growth rings of ancient coral that recorded the length of days in an ocean that existed before anything with eyes had evolved to see it. Every layer of rock is a page. Every stripe of polarity preserved in seafloor sediment is a sentence. Every coral skeleton from 400 million years ago, with its 400 growth rings per year telling us the days were shorter then, is a paragraph in a story that was being written long before the first human being stood upright and looked at the sky and wondered what was up there. That library has been patient. It has been waiting for something with the precision to read it. And now, for the first time in the history of life on this planet, something does. The atomic clocks, the radio telescopes, the gravity-sensing satellites, the magnetic field constellations, the global seismograph networks, all of it together constitutes the first instrument sensitive enough to read the planet's own record in real time while the next page is still being written. What the library says about where we are right now is not comfortable reading. The geological record contains multiple periods during which Earth's geophysical systems changed simultaneously. Periods when the rotation shifted, the magnetic field weakened, the ice redistributed, and the deep interior reorganized within a relatively compressed window of geological time. These periods left signatures in the record that researchers have spent decades learning to read, and when they compare those signatures to the current instrument data, the overlap is not approximate. It is specific enough to be informative. The period spanning roughly 500 million to 450 million years ago is one of the most studied of these convergences. Earth's rotation was faster then, days running approximately 22 hours, the planet spinning through its cycle in less time than it does now. The magnetic field was in a period of elevated reversal frequency, flipping more often than average, suggesting a dynamic and unstable outer core. The ice distribution was extreme, swinging between one of the most severe global glaciations in Earth's history and rapid warming phases that reshaped ocean chemistry within geologically brief intervals. And the biological record from that period carries the imprint of what happens when multiple geophysical systems change at once. The end Ordovician extinction, one of the largest mass extinction events in the history of complex life, unfolded across that window. Roughly 85% of marine species were eliminated across a series of pulses that paleontologists have been working for decades to fully untangle. The connection between the geophysical conditions and the biological outcome is not a simple causal chain. The extinction had multiple drivers: glaciation, sea level collapse, ocean anoxia, disruption of marine chemistry. Each contributed. The rotation and magnetic field changes were part of a coupled system whose components all moved together, and the movement of that system created conditions that life as it existed at the time could not fully absorb. That is not a prediction for the present. The biology of today is different. The geography is different. The timescales are different. Drawing a direct line from the end Ordovician to the present day would be scientifically irresponsible, and this story has no interest in irresponsibility. What the comparison offers is not a prophecy. It is a sense of scale, a reminder that the systems now in motion are not trivial, that the planet does not move between geophysical states without consequence, that the infrastructure of living systems, biological or technological, that was calibrated to one state, does not automatically transfer its resilience to the next. The last glacial maximum, the most recent period during which Earth's geophysical systems shifted in ways broadly comparable to what is being measured now, ended roughly 15,000 years ago. The great ice sheets of the northern hemisphere began their final retreat. Enormous quantities of meltwater entered the ocean. The crust beneath the retreating ice began to rebound. Sea levels rose. The rotation responded. And within that transition, there were moments of abrupt change that the geological record captures in extraordinary detail. Meltwater Pulse 1A, occurring roughly 14,500 years ago, raised global sea levels by approximately 14 to 18 meters in a span of 300 to 500 years. The redistribution of that volume of water in that time frame was large enough to produce detectable signatures in rotation models. It was not gradual. It was not smooth. It was a pulse, a rapid reorganization of planetary mass triggered when a threshold was crossed in the ice sheet configuration and the system lurched to a new state faster than the preceding trend would have suggested. Threshold crossings are the dangerous part of any geophysical transition. Not the slow approach, not the gradual drift away from the previous equilibrium. The moment when a feedback that was building quietly reaches the point where it becomes self-sustaining, where the change produces conditions that accelerate the change, where the system stops responding proportionally to the forcing and begins responding to itself. Researchers studying the current state of the West Antarctic ice sheet have identified configurations within the glacier dynamics of specific basins where precisely this kind of threshold behavior is possible. Marine ice sheet instability, the process by which a glacier grounded below sea level can enter a self-sustaining retreat once a critical geometric threshold is crossed, does not require ongoing external forcing once it begins. The physics drives it forward independently. Several research groups have published analyses suggesting that specific basins in West Antarctica may already be past their stability threshold, locked into a retreat that will continue regardless of what happens to the forcing conditions above. The timeline for how that retreat unfolds ranges across the literature from decades to centuries, but the direction appears settled. If that retreat produces meltwater pulses comparable in scale to what the geological record shows from the last deglaciation, the rotational effects will not be gradual. They will be episodic. Abrupt redistributions of mass that the correction infrastructure was not designed to handle at that rate or that magnitude. And the core dynamics feeding the rotation from below are operating on their own timeline, independent of what the ice does above. The three theoretical frameworks described in the scientific literature, the core-driven model, the ice-atmosphere coupling model, and the electromagnetic coupling model, each tell a different version of the same story. Each identifies a different primary driver for the surface acceleration. Each makes different predictions about how long the acceleration will continue and what follows it. What all three share is the recognition that the system is not in a transient fluctuation. It is in a departure. A sustained multi-system departure from the baseline that human civilization was built inside. The core-driven model predicts that the acceleration will continue until the angular momentum transfer from the decelerating inner core is complete, then stabilize or reverse over a timescale of decades. The ice-atmosphere coupling model predicts that the acceleration will track Arctic warming, continuing and potentially intensifying as the feedback between ice loss and atmospheric circulation strengthens. The electromagnetic coupling model, the most speculative but not without physical grounding, predicts that the acceleration is a symptom of a weakening magnetic coupling between the outer core and mantle, and that it will intensify as the coupling weakens further before reversing when the field transitions to a new configuration. Each of these trajectories ends somewhere different. Each implies different timescales and different magnitudes for the systems that depend on a predictable planet. But all three end at the same fundamental conclusion. The equilibrium the planet finds on the other side of this transition will not be identical to the one it left. The new state is not the old state with different numbers. It is a different operating regime. And the infrastructure of human civilization, calibrated to the old state, will need to be rebuilt for the new one. That is not an argument for despair. It is an argument for honesty about the scale of the adaptation required. The International Earth Rotation and Reference System Service is publishing Earth orientation parameters more frequently than at any previous period. The corrections required are larger. The rate of change in the parameters is faster. The engineers maintaining satellite navigation systems are applying updates more often. The modelers projecting the future behavior of the polar drift are working with a planet that is outpacing their models. The researchers studying the inner core are waiting for the next generation of seismic data that will either confirm the reversal or complicate it further. The magneticians watching the South Atlantic anomaly are tracking its expansion in real time with instruments that did not exist 20 years ago. All of them are doing the same thing. They are watching a planet in transition and trying to read far enough ahead to give the systems that depend on its stability enough warning to adapt. That is the function of science at this scale. Not to prevent what the planet is going to do. The planet does not take requests, but to understand it clearly enough, early enough, that the systems built on top of it can be adjusted before the gap between what was assumed and what is actually happening becomes too large to bridge. The question sitting at the center of every model, every research program, every quiet conversation in geophysics departments and geodesy laboratories around the world is the one this entire story has been building toward. How fast? Not whether the transition is happening. It is. Not whether the systems are coupled. They are. Not whether the consequences for infrastructure are real. They are, and they are already accumulating. The question is the rate. How quickly is the planet moving toward its new equilibrium? Is this a transition that unfolds across centuries, giving infrastructure time to adapt generation by generation? Or is it a transition that has threshold crossings embedded in it, moments where the rate accelerates abruptly, and the window for managed adaptation closes faster than the institutions responsible for it can respond? The honest answer, from the researchers closest to the data, is that the uncertainty around that question is larger than it was a decade ago, not smaller. More monitoring has produced more evidence of change, not more evidence of stability. Better models have produced better resolution of the mechanisms, and better resolution has revealed how tightly coupled the systems are, which means how much a change in one can drive changes in the others, which means how much the trajectory can diverge from any single system projection. The planet is not broken. It is not dying. It has been through transitions that make the current one look modest, and life has not only survived, but diversified through them. The geological record is ultimately a record of resilience, of systems that were disrupted and found new configurations and kept going. Life kept going. The planet kept going. The geodynamo kept going. The rotation kept going. But the thing that kept going through those past transitions was not GPS, was not a financial system synchronized to microsecond precision, was not a global power grid balanced by atomic clocks, was not hospitals full of equipment that fails on a 1-second discontinuity. The thing that kept going was biology, chemistry, the deep patience of organisms that measured time in generations and continents in millennia. Those systems are robust against geophysical transitions because they evolved inside of them. They are built for a planet that changes. The infrastructure of the last 10,000 years is not. It was built for a planet that stayed still. And the planet, as it has always done, across every period of stability that the geological record preserves, has eventually stopped staying still. What comes next will be written in the same medium that everything before it was written in. Rock, ice, the magnetic minerals of cooling basalt, the coral growth rings of oceans not yet formed, and somewhere in that future record there will be a layer that corresponds to right now. A layer that some instrument, or some intelligence, or some patient scientific tradition will one day read and understand as the moment when a civilization first had the tools to see the transition coming, to measure it in real time, to understand what was driving it and what it was likely to produce. Whether that layer will also record that the civilization used that information wisely, whether it adapted its infrastructure in time, whether it closed the gap between what its systems assumed and what the planet was actually doing. That part of the record has not been written yet. It is being written right now, in the rotation of the planet you are standing on, in the movement of ice you cannot see from where you are, in the churning of iron 3,000 miles below your feet, in the dark, in the heat, in the pressure, turning in a direction that nothing above it asked for, sending a message upward through the layers that will not arrive at the surface for years. The instruments are running. The data is coming in. Every atomic clock, every radio telescope, every gravity-sensing satellite, every seismograph station in a remote valley chosen for its geological stillness is listening. They are listening to a planet that has been speaking continuously for 4.5 billion years. They are the first instruments in that entire span of time precise enough to hear it clearly. What the planet is saying, in the patient language of milliseconds and magnetic field intensities and polar drift vectors and seismic wave travel times, is something it has said before, many times. In every period of the geological record where multiple systems move together toward a new configuration, it does not say it with alarm. It does not say it with urgency. It says it the way old things say important things, slowly, without repetition, trusting that something eventually will be listening carefully enough to understand. The planet is changing. It has changed before. And what comes after the change is not the end of the story. It is the beginning of the next one. If this kind of science reaches something in you, the kind of knowledge that makes the ground feel different beneath your feet and the sky feel closer above you, then nocturnal space is where you belong. Every video on this channel is built the same way this one was, from the data outward, from the deep interior of the planet to the edge of the observable universe, from the confirmed measurements to the questions that do not yet have answers. Subscribe to Nocturnal Space. Turn on notifications so nothing passes you by. And if this video found you at the end of a long day, if it gave you something real to carry into sleep, leave a comment below with the word iron. Just that word. So we know you were here, so we know you heard it. The instruments are still running,